The scientific revolution starts now.
This is the Science Joy Podcast.
Let us see in the dark.
So listen, we invited you back. It's been a long time since we saw you, first of all. And I think that in some sense, for a long time for us. So we've done almost 200 episodes now.
Right.
Long time for us. So I think that in some sense plays into the confusion here. So you somehow caught wind of our episode with Richard Lindzen. And
Which I'd like to imagine that you've been listening to our podcast ever since you were on.
yeah, hopefully you're just a dedicated listener and you're listening to all of them. But yeah, you reached out to us and you thought that we had terribly misrepresented some of your ideas from previously, and so we don't want to do that. First of all, I really don't want to do that. So I asked you to come back, and you did, and I really appreciate you coming back because I think that's the absolute best way to set anything straight about these things. So yeah. Welcome back. Thank you, and
thank you for
let's clear this up.
Yeah, thank you for giving me a chance to come back. So I unfortunately I don't have a huge amount of time to keep up with all of the most interesting podcasts that exist, and I'm sure that yours is one of them. But I noticed this because at some point last week I'm being showered with Twitter messages claiming that I admitted that the focus on carbon dioxide was just to maintain some kind of climate hysteria, and that you were being quoted as stating that. And then I tracked down the source of that, and you didn't quite say that, but it was along those lines. And then there was a lot of like kind of the interaction that you had with Professor Lindzen. Was a little bit odd, and I am, I get that, when somebody's on, you want to be nice to them and you want to go along with what they're saying, but he started making some quite personal comments about me that are not justified. I don't really know him very well. I've met him many times, but I don't really know him, and kind of like weirdly distorting things that not just I've claimed or that the rest of the scientific community has said. It was a little bit odd, and I thought that what would be nice is, if you do have questions about these things, and it's not really just a question about my ideas. Like I'm not trying to pretend that I'm a guru of climate and that everybody should go with whatever my opinion is. But if you have questions about why the mainstream of science thinks the way it does, or what the evidence is for why we think climate change is happening, what we think the consequences are going to be, I'm more than happy to be a kind of a funnel for those ideas. And it was just a little bit odd, I think Anastasia, you kind of put in a plug for me not being boring and having good ideas, which I thought was nice. But it's not really about me, and Richard Lindzen's kind of somewhat quite outdated views of what the situation is, kind of stem from a long history of having engaged with these ideas and had things not really work out in his favor in terms of the science. And there's a little bit of context there that I think might be useful for people watching.
So it sounds like there's a couple of things there that we should probably give the luxury of depth to. One of them is Lindzen's ideas. And that might be a good place to start. And the other one is our comment with respect to the importance of CO2 and the general environmentalist narrative and so forth. And maybe we get to that one a little bit later, because I think that requires some context in terms of what's going on in the discussion today.
Okay,
so,
those are two great topics. I'd be happy to engage on those.
So maybe we can just start by, can we just steelman Lindzen's presentation a little bit and just try to understand what, because he makes a very technical argument from what I can tell, which is something to the effect of greenhouse effects are most important at the equatorial regions, and that you have these Coriolis effects which predominate the dynamics and the mixing away from there. And so the things that are happening at the poles don't really depend on the greenhouse processes. That's like the 30,000 foot view from what I can tell. And then, of course, he brings in a lot of political arguments for the motivation for alarmism and so forth.
Let's skip over that. I mean, I mean, we could have a discussion about his political worldview, but let's move on.
Right on.
So you know, his argument was, you know, the tropics kind of stays where it is, and just the poles flip around, and everything that's going on is the poles, and that's not really anything to do with the greenhouse effect. That's based on discussions and data sets that were available in the 1980s, right? And a lot of what Lindzen talks about relate to questions that existed in the 1980s, right? So in the 1980s, we didn't have great models, right? So we had the beginnings of climate simulations. We didn't have great information about how things had changed in the past. You know, we had some information about how things had changed, but given, you know, where we are in from the 1980s to the 2020s, that's 40 years more of information that we've been able to pull out of ice cores and tree rings and cave records. All of those things didn't exist back in the 1980s. And it was still unclear whether the impacts of increasing greenhouse gases was going to have a serious effect on temperature. So this is what's called the climate sensitivity. So how much does the climate warm if you increase the amount of carbon dioxide in the atmosphere? And so we kind of like shorthand all of that into a simple number, right? So it's like, what was the climate sensitivity? And people for a long time have thought it's around 3 degrees. But you know, some people have said, no, it's much smaller. And some people have even said, no, it's much larger.
And what does that mean? Just really quickly, what does that mean?
Yeah,
3 degrees.
So if you were to take it's a counterfactual, right? So if you were to take the planet as it is now and instantaneously double the amount of carbon dioxide in the atmosphere. So, you know, so in the pre-industrial it was like 280 parts per thousand, and you would double it, so that would give you 560 or parts per million.
Parts per million, yeah.
Parts per million. And then you would just like kind of see, well, what happens? And so what happens is that suddenly it's harder for the energy to get out, so less energy leaves than comes in, so the planet as a whole warms up, the oceans take up most of that heat, the water vapor changes, the ice melts, the clouds shift, and eventually, you know, in a model, what you get is you get a change in temperature after you know, we generally run it at like 150 years or something like that. And those changes of temperature are around 3 degrees, right? There's a range.
At 150 years.
Yeah, after 150 years. But that's a very extreme perturbation, right? So the real world hasn't done that, right? So the real world, everything is kind of ramped up very slowly, relatively speaking, and so we are getting now. We're not close to doubling of CO2. We're about 3/4 of the way there if you include everything. But it's a much slower process, and things are happening much more slowly. So we use that climate sensitivity as a metric, just to kind of try and get that from the observations, try and see what different models do with different parameterizations, different kinds of clouds and things like that. So this number, right, is kind of important. And back in the 1980s, there was there was a group of folks that did an expert elicitation, and they went around and they asked all the scientists who were working in this, what do you think the number is? And people gave a range, and like I think they asked like 16 people, and 15 out of 16 of them said something around 2 to 4 degrees, right, which is pretty much the mainstream view.
And are they working off of different models, or are they? This is
so this was kind of lots of models, so there were a couple of models there, but people didn't think that they were necessarily the best models or they couldn't be improved, and so people were using, their intuition or their knowledge about cloud processes or water vapor to make, to kind of like take that in, but then kind of make an expert judgment.
So there's a number of free variables in those models then.
Yes, yeah, absolutely. But people generally thought that 2 to 4 degrees was about the right number. And then there's one person in that elicitation who said it was half a degree. And not only did they say it was half a degree, but they said there was no uncertainty. Right. Whereas everybody else said, well, it's like 2 plus or minus or 3 plus or minus, But then there was one person that said, no, it's half a degree and there's no uncertainty. So who was that, do you think?
Well, I assume, given the context of this conversation, that the answer is going to be Richard Lindzen.
Yes, you're right. Now, why is that interesting? It's interesting because there are certain consequences of whether that's true or whether the other folks were right. And one of those things is that at the time, like we didn't know what the answer was. At the time, it was that if the climate sensitivity is large, right? If the clouds don't cancel out everything that's happening with carbon dioxide, we expect that there will be an energy imbalance, right? That there will be more energy coming into the system than leaving. Right? Now, if the climate sensitivity was small, then that imbalance would be small and it would be very easily fixed by just a little bit of warming at the surface. Right. And so one of the consequences of a low climate sensitivity, no problem climate sensitivity, is that we wouldn't see a big imbalance. And we didn't know at the time what that answer was going to be. And so that was a prediction. Right. So the people that were saying, no, climate sensitivity is significant, were making a prediction, and this is very clearly articulated by Jim Hansen at the time. He said, we're making a prediction that we will see a large increase in the amount of heat in the ocean, because that's effectively the only place where you can store a large amount of heat that's coming in, right? And folks like Lindzen, who said, no, there's no climate sensitivity, or it's very small. Effectively, they're saying, well, no, you're not going to see an increase in heat in the ocean. And this was before we'd really pulled that data together, and before what we have now, the Argo floats and satellite observations of the surface temperatures. We didn't know what the answer was, right? But by the year 2000, and certainly by the year 2010, when a few more wrinkles had been worked out, what we found is there's an absolutely massive increase in the amount of energy in the ocean. And that's totally incompatible with the notion that climate sensitivity is close to zero or is negligible.
But there's a huge amount of turnover from the cold water at the depths of the ocean to the surface, and that happens very, very slowly. And so the amount of energy that's getting absorbed at the surface is then going to get mixed over time with the cold water that comes up. And so if you have this cyclical process, but you're seeing warming at the surface, that doesn't necessarily mean that there is warming 100%, because you're going to have cold water that's coming up, right? And so you have a constant sink.
Right.
Hey folks, we really need your help to keep this project going. Please come over to patreon.com and consider giving just a couple dollars a month to keep powering our spaceship. Because without that, we just can't keep up the quality that we've been delivering, and we want to improve that quality. And actually, by joining that Patreon community, you're going to be able to access our face-to-face chats every week. Tell us what we're doing wrong. Tell us what we could do better. Bring us guests. Let's make this a really, really powerful project together. Also, share the episodes with someone that you think will enjoy it, because that's what guests look at when they decide whether they're going to do our show or not. Like it or not, people want to be seen. And so as we grow this audience, we have access to better and better conversations. And that's really, really easy for you to do. So make sure to subscribe to the channel if you haven't already. Give us a good review over at Apple or Spotify, and share it. Leave comments, come over to Discord, talk to us, tell us your thoughts, and let's make this a better project than it already is. Also, next April 7th and 8th, we are having our first Demystify Sci conference. It's going to be a pretty incredible lineup. Our keynote speaker is Pierre-Marie Robitaille, who is championing this revolution in astrophysics concerning the material nature of the stars. And there's a number of other speakers on topics ranging from mythology to economics and everything in between. So you're really going to want to go over and grab a ticket right now. And we will hang out there and we will catch up on what to do about the world in the future and how to explore it better at the Demystify Sci podcast. Back to the conversation.
Yes, but it's not. But it can't take up heat indefinitely without getting warmer itself. And so what we're seeing is that the warmth in the ocean is increasing near the top where everything is mixing down, and then it's also increasing in the intermediate waters where stuff is kind of coming from the Southern Ocean, and it's warming at depth, even at the level of 4,000 meters. We're seeing warming in the ocean, and we know that that's right because the ocean is expanding as well, right? So we can tell that the sea levels are rising. We have satellite altimeters that measure the sea level to in the global sense to within a centimeter. And we're seeing this rise. And when we add up all the bits, how much of the ice is coming in, melting from the glaciers, from the ice sheets, how much of the ocean is warming, it all fits together. And so we have a very consistent picture of what's happening that only makes sense if climate sensitivity is non-negligible, right? And Professor Lindzen really doesn't ever engage with the more modern information there. And so, he's still talking about the iris effect. He's still talking about cloud feedbacks when it's clear that cannot be the right answer.
I mean, it's still not clear to me, like you're saying that there's this measurable warming of the ocean and, great or not great, actually, as it may be. But
magnitude, yes.
But pegging that to this molecule, I think, is really the question that we haven't gotten to.
That's a great question. So the increase of energy in the ocean tells us that there's an imbalance in the energy budget of the whole planet, right? So there's more energy coming in than leaving. Now, there's multiple ways that you could get that. Right, you could get it because the sun was brighter. Right, so if the sun was brighter, then we'd have more energy coming in, and there'd be less leaving, and so we'd be accumulating energy. Right, so that's a valid that's a valid hypothesis at the outset. And then there are other things that could be changing. You could say, well, maybe we're deforesting, and that's changing the surface energy balance, and that's having an effect. Or there are pollutants like soot or other kinds of aerosols that we're putting into the air that are changing the energy balance. But these things have to be big, right? So
we also realize that these cycles naturally occur too, right? So that whether it's Milankovitch cycles or something, there is some very regular, constant shifting of these temperatures over time, right?
Right.
So we're definitely on the upswing of that.
Well, not of Milankovitch. So if you look at the Milankovitch parameters, we would actually be cooling, and we're kind of bottoming out of a cooling cycle that's lasted since the mid-Holocene. So around 8,000 years was the peak insolation at 60 north, and then it's been going down since then. But you have to remember that Milankovitch is on time scales of 20,000, 40,000, 100,000 years, right? So we've not detected any anomalous wobbles in the Earth's orbit that are not explained by what's happening with the standard orbital cycles. And so when you're looking at what's happening, in the last 150 years, where you've seen this very rapid warming, it's the wrong sign for what you would expect from Milankovitch, and B, it's happening way too fast. So there's a real mismatch between the expectations from Milankovitch and what we're actually seeing. But you're right. There are cycles, right? So there are solar cycles, right? So we can see these 11-year solar cycles, but we've been measuring those, right? So again, this is something that in the 1980s we didn't have great data, right? But now we have over 40 years of satellite measurements of the insolation from the sun, how much energy the sun is bringing in. And it hasn't changed by some massive amount. It's gone up and it's gone down with the solar cycle. Right now, we're just going into a solar maximum, but this solar maximum is not as big as the last couple of solar maximums. So overall, we've actually been getting less energy from the sun since the 1950s, as far as we can tell, and so that doesn't help us explain things. But then there's also you mentioned, okay, well, how do you know it? Carbon dioxide, of all the things, right? Lots of things have been changing, right? So how do we know that's the cause? Well, it turns out that each of the different things that could be causing a problem or could be causing this change have different fingerprints, right? And some of them have very unique fingerprints. So if you take a climate model, and you say, okay, well, let me increase the carbon dioxide, or let me increase methane, let me increase or decrease the amount of particulates in the atmosphere. They generally have patterns of responses that are recognizable. So if you increase the amount of carbon dioxide, you get a little bit of warming in the tropics. You get more warming at the poles, right? We mentioned that earlier. And you get warming in the troposphere, right? So that's kind of up to the level of where the weather is, where the big convective clouds is. And then above that, in the stratosphere, where the ozone layer is, you get cooling. And it turns out that that's very special to carbon dioxide. You don't get that with methane. You don't get that with aerosols. You don't get that with the sun. But this pattern of warming below and cooling aloft was something that was predicted by Minabe and Weatherall. So this is going back to the 1960s. And Minabe won the Nobel Prize for physics in large part because of that paper. And they published that in 1967, and they showed very clearly that if you take into account all of the different spectral elements of carbon dioxide and water vapor and all the rest of it, then carbon dioxide would lead to a cooling in the stratosphere.
But not water, right?
Water, no. Water, so the stratosphere is very dry, and so water vapor changes are almost all in the lower part of the atmosphere. Though there's a couple of exceptions we could get to. And so you don't get that if something else is going on. And so again, like in the 1980s, we didn't have long time series of temperatures in the stratosphere, but now we do. Now we have 40 years of temperatures in the stratosphere. And what are they doing? You can guess. Are they cooling or warming?
Well, based off of the glee on your face, I would suggest cooling.
Yes, you would be correct. It's not glee. It's funny. I take absolutely no pleasure in the fact that mainstream climatology is correct. Like it's a disaster. Right. I don't want our predictions to be correct, but I do want us to understand why those predictions come from, where they come from, and what that means. But it isn't like like we're chatting here, and okay, like there's a little bit of banter, but really we're just it's, we're partying before the storm here, right?
I mean, before we move on from this, I was looking at some of these curves of the glacial periods and the temperature change over the last, say, 500,000 years or so, and it looks like the temperature was certainly more maxed out in the last interglacial period than it is today.
That is true.
And it looks like in general, if you they're kind of these little sawtooth spikes, and then the glacial periods seem to be sort of much longer with this, downstream. But I wonder, in some cases, it appears that there is some hysteresis, like the maximum. Maybe you have maximum solar energy coming in, but it takes a while for things to warm up after that. Do you think that could...
Yeah. So I think that's very likely to be true. The interglacials kind of come on a roughly 100,000 year timescale, and they last between 10,000 and 50,000 years overall. So the last interglacial was actually relatively short compared to other interglacials. So that one's called the last interglacial. Also stage 5e, and each of the like stage 7, stage 9, stage 11, they're those other interglacials, they're those peaks. And what happens there is that depending on exactly how the eccentricity and the obliquity and the precession line up, you can have very, very fast overshoots and then come back down, or you can have broader, less dramatic changes. And so stage 11, people think lasted maybe 50,000 years, maybe even longer, because things were moving slower, and so when the precessional cycles, which are the fast ones, came along, it was able to stay deglaciated for multiple precessional cycles, whereas for the last interglacial, it only deglaciated for one precessional cycle. So it was a very short and sweet event. But it's clear that that particularly in the Arctic, it was warmer at the last interglacial than it has been yet so far this interglacial. So yeah, I mean, there's some very interesting patterns there, and there's lots of high frequency relative. So this is the thing: high frequency for glacial period variations. That means 1,000-year type oscillations in the record that are associated with big iceberg events in the North Atlantic, oscillations of the overturning stream function in the ocean. Absolutely fascinating dynamics. But again,
it's not very clean, right? This cycles aren't. We would love to think that it's perfect sawtooth, but there's a lot of variation in the way that these curves shape up, assuming that they're interpreted correctly from the data themselves. But
yeah, I mean, we have again, one of the things that's new is that in the 1990s, when we first really started to get those ice core records, that really changed everybody's view about what could possibly happen. There was a lot more noise in that than there had been in the previous data, which had been taken from relatively low resolution ocean sediments, right? And a lot of things were smoothed out in that data. The ice cores gave us a much finer view of what was happening at what time.
Yeah, can you break that down? Actually, I had a friend actually call me up and ask me the other day how it was that you determine temperature from an ice core, and I understand it a bit in terms of the oxygen isotope ratios, but maybe you have a very clean way of explaining that to people who don't understand, because it is a secondary readout from. You're not just measuring CO2 inside of these ice cores, or you don't get a thermometer readout from them directly, obviously.
Right. So the isotopes are very interesting. And in fact, my all my postdoc work and all of my actual good ideas in terms of how to understand stuff was related to oxygen isotopes, which is kind of
perfect.
So the idea is that oxygen comes in multiple flavors, right? So the two main ones is oxygen 16, which is most of it, and then oxygen 18, which is slightly heavier. And chemically, they don't really make any difference. But when things change phase, it turns out that when you want to condense water, the heavy water condenses first. Right, or when you want to evaporate water, the light water evaporates first, and so as things move around, so in the water cycle, we evaporate things basically in the tropics and subtropics, and then it gets advected to the pole, and then you lose water as you get towards the colder parts of the planet, and so depending on the temperature, you lose a certain amount of the heavy isotope. So when you get snow that's landing on Greenland, what you see is that the colder it is when it's snowing, the less oxygen 18 there is, right? The heavy one, that's gone. And so it's mostly oxygen 16. And so when you look at the ice core going down, which is effectively going back in time, what you see are these peaks and wiggles of the oxygen 18 curve that correspond to warm phases and cold phases. Now,
Are there any other factors though? Just to
sure.
be absolutely sure. Like, is there anything else besides temperature that's going to affect those? Precipitations?
So where the water is coming from makes a difference, right? So if the water is coming from the Pacific, it's gone further and more stuff has drained out than if it had come from the Greenland Sea. So if the proportion of water from the Atlantic to the Pacific has changed, then that would give you a signal in the O18 as well. Changes in seasonality, right? So during the last ice age, it very rarely snowed in the wintertime on Greenland because it was too cold, right? So it was more desert-like. And so the seasonal cycle was different. And so that imparts a kind of rectified effect on the oxygen 18 as well. And so calibrating those wiggles going back in time has been a bit of a saga, right? So there was the initial calibration, which people thought, well, that's probably okay, but it turned out to be wrong by about a factor of 2 compared to what we think now. And the way that we were able to better calibrate that was some really neat geophysics where you had very, very sharp changes in temperature. And it turns out that in a column of gas, when you have a very sharp change of temperature, there's a settling effect, but that only happens when things change very quickly. And you can detect that with the isotopes of nitrogen in the column. And it turns out that you can calibrate the oxygen 18 thermometer against these isotopes of nitrogen, and you get a different calibration than people had thought, and actually one that makes a lot more sense.
And it's not as sensitive to travel distance. The nitrogen?
No, so it turns out that it's a totally independent and it's a purely local test. It doesn't depend on anything else, and so you are able to use that to calibrate the oxygen 18 where something quickly where something fast happens, and so you can do that. All of those big wiggles in the ice age, you could do that. You could do that every so often there. The Younger Dryas event, you could do it there because things changed very quickly, and so you could use that to calibrate it. And then that changed the calibration a little bit, and so we got a better view of exactly how many degrees per change in the oxygen 18. But this gets quite technical quite quickly. But the interesting thing is that after many years of this, we have multiple ways of doing this now. We have that different calibration. We have speleothem records. So these are cave records where you look at the stalagmites kind of building up. And each of the layers, they're made of calcium carbonate. So calcium carbonate, CaCO3. It turns out that the O's, which also have O16 and O18 in them, the fractionation of that depends directly on the temperature in the cave. And so there's a little bit of a signal from the rain because that can change as well. But those records from the caves line up really, really well with the ice cores, and very then cool. Go and do multiple.
That's actually I've spent an inordinate amount of time in caves, and they're not supposed to vary relative to surface temperatures very much. And so that's
exactly right. So if the surface temperature changes on long time scale, then that eventually gets into the cave.
Well, that's what I'm trying to say is that their temperature is supposed to be not equilibrated with the surface temperatures.
But it is. But over a long time, you lose the seasonal variation, for instance. So caves are warm in the winter and cool in the summer, but they generally respond to how warm the Earth is above it over very long time periods.
But they also react to how warm the Earth is below them as well, right?
That doesn't change so much. So the geothermal flux in most of these places is not varying on a century by century basis. That's driven by very deep things going on in the crust, and that does not change very quickly. But then you've also got the signal from the rainfall. So the signal from the rainfall actually in a lot of these places is the dominant term. But you look at these things and they line up. So you've got these set of caves in China that every time there's a big event in the North Atlantic, right, and the ice cores do this, they do that as well. And so you're seeing these kind of like downwind imprints of, in this case, for instance, variations in the overturning stream function in the North Atlantic, the ocean, the part of the ocean circulation that's kind of like goes with the Gulf Stream and then kind of like goes down in the Norwegian Sea and the Greenland Sea. These things are all connected, and we have a much better view now of what's going on and what makes up these records than we had in the 1980s.
So this might be a good point to bring up another issue that you'd mentioned when you initially emailed us. And so there's this somewhat regular sawtooth that, let's assume that this mapping of temperature data onto the past is decent for the purposes. I mean, you've done a pretty good job to at least justify that belief. I think that it's reasonable in what you've said. So we have this sawtooth pattern. And I remember, of course, memory is a terrible thing to lean on, but I had remembered that the last time we talked, I mentioned, okay, well, these interglacials are generally pretty short. Usually the downslope in the glacial period lasts a long time. So, this interglacial that we're living through right now, it should be over pretty soon, and things will start getting cold again, and eventually the poles should, regularly freeze over, and this won't be a problem anymore. And you said something to the effect of, no, that's not going to happen. And, of course, my memory filed that away as that's not going to happen ever. But I went back and listened to it, and you actually said that's not going to happen like it had, essentially, is what you were trying to say, and that we shouldn't expect it for 50, 100,000 years, something like that, which would be much longer than generally for the other interglacials in the past. And so I just wanted to get the chance to set the record straight on that.
People, as soon as people worked out that the last interglacials were paced by Milankovitch back in the 1970s, people saw how long the last interglacial had been, which was about 10,000 years, and they saw how long the Holocene had been, and they said, "Oh, it's about 10,000 years. Oh my gosh, we're due for another ice age." And there was a little, maybe a cottage industry of folks that started looking for little ice ages everywhere. So it cooled from the 1940s to the 70s. Oh my God, there's an ice age starting, and there was there was one other thing, I can't remember what it was, but that notion was predicated on the idea that we knew exactly how this interglacial was going to go in the absence of us, and that was not actually clear at all in the 1970s. I think we have a better sense of what we would have expected now. And so without us, I think the consensus is, though not a huge number of people work on this, so that's probably not worth very much. But the idea is that we probably would have skipped. It would have gone up like this, gone down, not glaciated, come back up again, and then maybe you would deglaciate on the downside of the next hump, right, which would put you in an interglacial of about 30,000 years.
And now we've never seen that before, though. But this is assuming...
we have. Yeah, so when you go back further, you see interglacials that lasted 30,000 years, and you see interglacials that last 50,000 years.
Like a million. This is a million years ago or something. Very long.
Well, I mean, going back over the last million years, right? So there's how many do we have good information for? We have good information for maybe 7 cycles, seven interglacials, and they vary in time. But they're kind of quantized, right? So it's either 10 or 30 or 50, right? Maybe you could have longer ones as you go back. We've been doing that. This has been happening for about 2.5 million years, and we don't have quite the resolution of stuff going back much before that. Bill Ruderman, quite famously wrote a couple of papers, said, no, we should have been in a new ice age by now, and in fact we hadn't. His theory was because of the emissions of methane and carbon dioxide from early pastoralists and people starting to do farming in, say, from the middle Holocene onwards.
But that suggests an enormous hysteresis, right?
Well, it suggests an enormous sensitivity to very small changes in greenhouse gases. So, people generally don't really think that. I think, but it's he pushed that quite strongly for a number of papers over a number of years. He's actually a fascinating person to have on, and if you want to have like a history and somebody making the pitch for that, he would be a great guest. He's written, the textbooks on this, and
You said Bill Runneman?
Bill Ruddiman, Ruddiman. I think he's retired now, but he may still be interested in doing something like that.
That's our bread and butter. Is retired scientists.
Yes,
Retired people have nothing to lose,
Yeah.
And so much time on their hands.
Well, there's that. Yes. Okay. So let me get back to whether we're going to see this happening. So let's imagine that either Bill Ruddiman is correct and that a small amount of carbon dioxide has pushed us out of an imminent ice age, or that the mainstream consensus is correct and that this interglacial was due to last 30,000 years or more. What's happened now, and how is that changing? Well, what's happened now is that we've warmed the planet by over a degree now, since the mid 19th century or so, and what we see everywhere is mountain glaciers in retreat. Right, we're seeing, there was just a story today. Alpine glaciers in Switzerland have lost like 10% of their entire mass just in the last couple of years. We are seeing ice caps in places like Ellesmere. They're retreating, and one of the interesting things that happens then is that where you have just that ice cap, where the snow is just kind of sitting there, it's not moving, it's not a glacier, it's just snow that never melted, and where it's melting now, you can try and carbon date the moss and the grasses that are underneath the snow, and it turns out that when you do that, they have no radiocarbon. Right. And if they have no radiocarbon left, that means they haven't interacted with the atmosphere for at least 55,000 years. Right. So that means that effectively those are relics from the last interglacial. And so we're seeing places in Ellesmere and the Canadian archipelago that are now retreating more than they were in the last interglacial, or at least the end of the last interglacial. And so all of those things are moving in totally the wrong direction, right? And so by the time that we're done, by the time that the ice sheets have come into equilibrium with what we end up doing to the planet, and we're not done with the planet, right? So it's not clear what that equilibrium will be yet. It will be the amount of cooling that you would need to have to get them to come back is going to be very hard, right? It's going to be too much for the Milankovitch forcing to be able to deliver. And so when people have done these kinds of simulations and they say, okay, well, here's what Milankovitch would be telling us would be happening, either like a 30,000 year or like a 10,000 or a 30,000 year interglacial, and then you put in the carbon cycle changes that we've made, and then you just wait for that to kind of like go through the system, which takes many tens to hundreds of thousands of years. Then you don't trigger a new ice age for a few cycles, and so the chances that we're going to ever see ever, I don't want to say ever. The chances that the next few precessional dips are going to lead to an ice age are much less than they used to be. And so my estimate, I don't know what a prediction for 50,000 years in the future is really worth. But my prediction, for what it's worth, is that we will not go into a new ice age in 30,000 years' time, and maybe not even in 50,000 years' time.
So something that is really central for me in all of these discussions is that I think that every single civilization that has ever ended and you could probably put an asterisk on that, but has ended because of climate change. Like, this is just I think that most of them that you look, it's like extended periods of drought or weird things start to happen. Maybe like with the Roman Empire, you could point to lead in the water, but in general, it seems that, okay, we grow up in a time where things are a certain way, there's a dramatic shift, and then civilization ends. And so from that, I look at it and I'm like, okay, so climate change is 100% absolutely the biggest threat to civilization because we are not optimized to deal with a planet that changes around us, because civilization by its very nature is a structure that has a ton of hysteresis. We do things this way, and we are going to continue to do things this way, and we will do so into the grave.
And we like to live in the lowlands by the water since
We
forever.
do. We love the water. And so, like,
I think something
Yeah. So
and most people live by the water, within 60 miles of the water.
and like, we know that sea levels have changed dramatically, and we know that civilizations are buried underneath the waves. And so it's like, all of these things are a given. There's this other piece of it too, though, which is that civilizations have spent a lot of time throwing virgins into volcanoes because they think that it's going to appease the gods and prevent climate change.
Yes.
And I see the monolithic focus on carbon dioxide as being a version of us throwing the virgins into the volcanoes because it is a molecule that can be targeted, that can be sequestered, and that indulgences can be bought for it. You can buy a carbon offset for the flight that you take. There are marketplaces for being able to buy and sell these things that allow you to change absolutely nothing about the way that you live.
Right.
And then to say, my carbon footprint is really small and it's okay. And I'm like, I think that's the thing that really alarms me about this. I don't have a problem with the science. I think that science is one of those things that you can pull together a really compelling narrative that's based on solid research. And my issue is not with the foundational research or the data. My issue is with the larger social structures of what this does to people and what it allows to continue, because I think that science is, at the end of the day, the only tool that a state has by which it chooses to do things.
Objectively.
Objectively. Like, we don't have God anymore. Like, in theory and in an ideal world.
Yeah. Well, I think you give science far too much credit in terms of controlling anything.
Well, the politicians love it, though, right? I mean, they're always scientists say and scientists say this.
Yeah.
Well, I mean, politicians and people love the products of science. They love the products of technology.
Oh, for sure.
And so, you're always wanting to take your idea and attach it to science because science has more kudos than just it's my idea, right? So you end up with this kind of weird, everybody wants to be like more scientific, but then when the science tells you that their plan is not going to work, or that it's like kind of give you the opposite effect of what they expect, then they're very keen on dismissing the science. So it's a little bit of a binary thing there. But I because people talk about science, I don't think that I think people just like back in the old days, people talked about religion a lot. People talked about God a lot, but really that was a cover for people's like kind of desire for power and desire to mess up other people's lives and desire for conquest and things like that. But it was all blamed on religion, and I think that what happens when you have a challenge to a civilization, like the environmental challenges that we've had, and carbon dioxide is not the first one that we've had. We had issues with dirty water, we've had issues with dirty air, we've had issues with ozone depletion. the same kinds of rhetoric emerge around each of those things. It's got nothing to do with the essence of what's causing it. It's got nothing to do with whether carbon dioxide is a particular molecule or whether you can do anything with it or not. People were saying very similar things about ozone. People were saying similar things about sulfur dioxide. People were saying similar things about PCBs in the river. I mean, they're not. The scientific quality of these threats is not what people then deal with. But you're right. People are going to want to make it go away, right? So they will prefer the status quo to doing anything about this. And so things that allow them to maintain the status quo are going to be favored over things where they have to change or where something becomes more difficult or you have to do something a little bit differently. And I think that's inevitable, right? We are creatures of habit, and we have a great deal of inertia. We don't want to change, right? And change is scary for a lot of people, whether it's economic change or technological change or just getting old, personal change, right? People don't like those things. And so when you come along and you say, well, this thing that we're doing is having a consequence that's much bigger than we thought, and that was true for ozone depleting chemicals. It was true for burning dirty coal. It was true for pouring continual amounts of shit in the water, literal shit. So people will say, well, it'd be too expensive to build sewer systems. It would be too expensive to clean up the coal. It would be too expensive to switch to a different kind of aerosol spray. And people
But
come
I
up
think
with
that those are
reasons
different.
not to
I
do
think
that.
that those are different. Like I think that those are different in kind, because if you just look at, let's say, C8, which is the shit that DuPont was dumping in the Ohio River, that they had paper after paper that said that they knew that it caused reproductive damage and had teratogenic effects, and they were taking pregnant women off of assembly lines and they were keeping it quiet, or whatever substance you can point to where there's a clear marker of toxicity.
Right.
There's a difference in the conversation around carbon dioxide, because it feels like carbon dioxide is something that if we took the pressure off the biosphere through our manufacturing, through our wastefulness, through I guide for when I'm not doing the podcast. I'm a backcountry guide. And so I'm part of the outdoor industry. And the thing that's crazy about the outdoor industry is that these are people who love nature. They love the planet. They love being outdoors. They take airplane flights everywhere for a few days. They package things in massive quantities of plastic. And at the end of the day, they dump everything in the trash. They get back on the plane and they fly away again. And I'm like, you can buy a carbon credit that will offset every single one of those things, and it will not change the fact that you have still trashed the planet, despite the fact that someone somewhere has planted some trees to cover for your carbon. Because the carbon is not the thing that's killing the planet. The thing that's killing the planet is everything else. And so I'm concerned that what happens is that when our focus is on carbon and is on rising global temperatures, what we're not taking care of is the fact that, hey, hold on a second, we have a planet that needs to be able to balance itself in the face of these changes. We have a civilization that needs to be resilient enough to deal with these changes. And the narrative is so focused on the monolith of this molecule that has that in and of itself does not have the kind of toxicity profile as the plastic that is in the Cliff Bar wrapper, or the rubber that is in the car tire, or the C8 that's being dumped in the barrel, or the petroleum
in the car tires, like 7 pounds or something.
Like, it's
no,
just
so you're
insane.
look, so you're right. Sustainability of everything is required, and climate change is not the whole part of that. Absolutely not. But climate change is a stressor on all of those things, right? It's a stressor on the ecosystems that you like walking through. It's a stressor on the water resources that maintain them. It's a stressor on the ski resorts that these folks will like to go to.
But the plants love it. To be fair,
sorry,
the plants love all that CO2. To be fair.
Oh, the plants, yeah, but
it's never been greener, right?
They'll only grow if there's enough water, and so, or if there isn't too much water and nutrients, and so all the carbon dioxide that you want to put in the atmosphere is still not going to make the Sahara bloom. It's one of those things that makes a difference at the margin where that was the only thing that was limiting growth, but most places that's not the only thing that's limiting growth.
But I think that's what makes it so tricky, is that it's not just this toxic molecule, right? It's not just some poison.
Well, I mean,
itself,
carbon
right?
dioxide, like the toxicity of carbon dioxide is neither here nor there. I mean, I guess if you were in a room of 20,000 ppm, then that's toxic. I don't know what the exact level is, but that's not why we care about carbon dioxide. We care about it because it's a radiatively active gas. It's not because it's biologically harmful. And the climate is big, and it affects all of these things.
Yeah, well, and to that end, you can't just get rid of it, right? You can't just get rid of, like, you're not trying to get rid of carbon dioxide. Also,
no, we're trying to stop it. I mean, the goal is to stop it growing anymore in the atmosphere, and to hopefully bring it back down a little bit from where it is. But no, I mean, obviously, carbon dioxide is a key part of the carbon cycle. Though we don't want to get rid of it. But when you have too much of a good thing, then it has these other effects associated with the climate, and that's why this is a different kind of pollutant. And so it's really unlucky, right? I mean, it's really unlucky that the temperature of the Earth is just at the point where carbon dioxide is a big absorber of infrared radiation coming from that temperature, right? That's just an accident of cosmic history. It didn't have to be that way. It's not inevitable that that was the case, and that we have all of these stores of fossil carbon just like sitting around waiting to be burnt. Those are like, nobody planned that.
Increasingly less of those stores, from what I understand.
Well, there's still a lot though, and more than enough to. We're talking about the Ice Age, So if we burn all the things that we just know about now, then that's enough to put us, effectively as warm again as the Ice Age was cold. Right. So that's
if we could find them and suck them all out of the earth.
That's the stuff that we know.
But it does seem like we've passed that. Do you think that we've passed the peak oil?
I would like to think so. And you see, we talk about tipping points. There are social tipping points. I think we're seeing social tipping points towards electric vehicles. In a lot of places around the world. Not quite in the US yet, but in Norway, more than 50% of new cars are now electric. And you're going to see that kind of spreading from Europe and Japan onwards. So yeah, I mean, to the extent that we mostly use. We mostly burn oil for transport, right?
But each of those electric cars, right, they depend upon oil to be manufactured. They have tons of plastics in them, and the tires are made out of oil, and the
roads are made out of oil.
The problem is not oil, right, per se. The problem for the climate is burning of oil and releasing carbon dioxide into the atmosphere. If you use oil as feedstock for plastics, which is a small fraction of the oil that's dug out of the ground, that actually doesn't really contribute to the climate problem, though it does contribute to your the problem that you raised in terms of trashing the environment and leaving layers of plastic everywhere in the world.
Go ahead. No, go ahead.
I just think it's like a much bigger problem if our entire material economy depends upon plastics, and plastics depend on fossil fuels. Not even the fuel side of things, but just the petrol itself. Right. That's something that we have to find workarounds for alongside of things too that really.
I mean, we can make plastics out of cellulose. We can make plastics out of pretty much any kind of organic molecules. I mean, oil is convenient, but like I said, like if you were just using oil to make plastic, you wouldn't be trucking oil around to anything like the extent that we're doing now, and B, the climate impact of that would be pretty negligible. So if that's if the issue is we still need oil for plastics and various high tech this, that's, and the others, fine. Like that's a tiny part of the issue. The issue for the climate is the burning of fossil fuels that produces carbon dioxide and a little bit of soot.
I completely understand. I just find it an interesting shared interest of both those two environmental camps. It seems like you're knocking out two birds with one stone by if you're fixated on the burning, if you're fixated on moving away from fossil fuels, you're also inevitably fixated on moving away from them in manufacturing and so forth too. If you've developed parallel energy sources and parallel ways of manufacturing, it just seems like there's a lot in common in those two narratives.
Because at the end of the day, like, we spend a lot of time in conversation with people that are very suspicious of narratives around climate change or whatever centralized scientific narrative is presented.
Mm-hmm.
And my central focus in those conversations is figuring out how to get people on the same page about the things that are really important. Because I think that it's not possible to move forward with some significant fraction of a nation being on the opposite side of a debate that everybody's like, that the other side is like, hey, we have to do this or we're all going to die. Like, I don't think that you can survive as a nation if 50% of people are like, if we don't do this, we're going to die. And the other 50% are like, no, we don't have to do anything.
Yeah. I don't think we're in that space at all. I think we're in a point where 20% of people understand and want to act preventatively to stop things getting worse, and then there's maybe 5 to 10% of people who vehemently don't want anything to change and spend a lot of time and are very loud, and then there's the vast majority of the people in the middle who recognize that there's a problem but don't really know what to do about it or how it fits in with their real world decisions. So
those tails are the ones that are shaping the discourse.
Well, I think that's true about any discourse.
Of course, absolutely.
The people at the loud ends frame the discussion, but we manage as a society with having quite loud and opposed voices on the edges, and the vast majority of people kind of just go along with something. I would like to think more moderate and sensible. Now, it's not the case that anything that is like in between the two voices is right. That's a terrible philosophy. But we've managed to survive with people being on individual people being on very opposed sides on many questions. But one of the things that happens though is that are we hearing this same discussion about ozone depleting chemicals? We're not. Were we hearing that in the 1980s? Yes. Very similar discourse was happening in the 1980s. The adverts in the New York Times, the polemics in Congress, the industry the industry-led talking points that were all scientific nonsense. The few scientists kind of standing up and saying, "Oh no, we need to do something about this." And at the time, you would have said, "Oh no, this is very highly polarized. How are we going to get past all this?" Well, we got past it because there were enough people who were sensible enough to make the right decisions that led to better improvements in the technology, that led to phase outs of the things, that led to legislation, that led to the Montreal Protocols. And effectively, we made that switch without any huge disruption to anything very much. And then it went away. It became not salient anymore, and yet we're still using deodorant, and we still have aerosol cans, we still have air conditioners, we still have fridges.
We also still have a
Don't we
hole.
still- yeah.
We also still have a hole in the ozone layer.
Always, but it's stabilized. Back there in the 80s and 90s, it was getting worse. Every few years it was getting worse. But like now, it's stabilized.
But it hasn't improved.
Yeah, I thought I saw it was making a comeback recently.
So the Hunga Tonga eruption, which put a lot of water vapor into the atmosphere, is probably going to make this October, and that's going to be a bad ozone hole year. But the levels of CFCs in the stratosphere have been coming down, and the level of ozone depleting chemicals has been coming down, and so we expect kind of by 2030, 2035 to actually see a very clear recovery in that. And that's a prediction I will be around to see. And so you can hold me to that.
Well, yeah,
we'll
that
have you
one's not
back in
making as much
2035.
press, which is interesting. But wait, that's really interesting. So how does the volcano affect the ozone?
Because the ozone depletion in the South Pole relies on chemical reactions that happen on small particles of ice, and so they're called polar stratospheric clouds. They only occur in the very coldest depths of the polar vortex, and that's mainly in the in Antarctica. But it's when there's more water vapor in the stratosphere, which as we mentioned before is a very dry place. And we've increased the water vapor by about 10%, which is quite a lot. So there will be more polar stratospheric clouds. There will be more ozone depleting reactions, and so there will be more ozone depletion in the this will be the spring. So this is as we're coming into the southern hemisphere spring now.
And we haven't talked too much about water actually, and I want to get your thoughts on that because water is a pretty decent greenhouse gas too, from what I understand.
Oh yeah. No, water vapor is about half of the current greenhouse effect. Yeah.
And how does that play out in the Holocene versus in the past? What's our current epoch look like?
Yeah, so the key thing about water vapor is that it has a very short residence time in the atmosphere. So if you see how much evaporation there is, how much rainfall there is, an average water molecule stays in the atmosphere for about 10 days. Right, which in terms of the perturbation time for carbon dioxide, which is on the order of thousands to tens of thousands to hundreds of thousands of years, gives you a sense of why they're treated a little bit differently. And so water vapor really just responds to what the temperatures at the surface are. So when it's warmer at the surface, then it's warmer in the air. The air can hold more water, and it holds about 7% more water for every degree warming. So we've already seen like 7% more water vapor in the atmosphere since the 19th century, and that has consequences for rainfall events and clouds and the like. And as we said, if it gets into the stratosphere, then ozone.
So this is a sort of positive feedback. This is part of the...
It's an amplifying feedback. So as it gets warmer, you get more water vapor. Water vapor is a greenhouse gas, so that makes it more warmer still. It doesn't like become bigger and bigger. It kind of like levels out. But yeah, so it's an amplifying feedback on really anything that would change the climate. So you would see the same feedback after a big volcano, and the water vapor would go down. And in fact, we see that. You would see it after, if the sun was brighter, you would see a water vapor feedback. So the water vapor it doesn't really care why anything is changing. It will just change with the temperatures, and so that's why we tend to see it as as a follower rather than a leader. So if we increase the amount of water vapor in the lower atmosphere, and we kind of do through irrigation, so if we irrigate a lot, then it's more moist immediately above the irrigation. But it doesn't take more than a couple of days for that to rain out and to equilibrate again. So we can have local effects on the water vapor deliberately, but the biggest change in the water vapor is because the temperatures are changing.
And doesn't the water vapor play into the cloud cover?
Yes, but cloud cover is not just water vapor, right? So cloud cover is the motions of the air, the waves in the air, the interactions with aerosol particles, and if you look at all the different places where different clouds form, there's 1,000 different processes that are involved in those things. It's not the case that if you increase the water vapor, then everywhere clouds increase. That's not how it works.
Mm. We had this really interesting dude, and his name's escaping me now. Nastia will probably remember.
Nir Shaviv.
Nir Shaviv, yeah, in Israel, and he had this theory that that there was cosmic rays that were seeding clouds essentially, and that this transit of the solar system around the galaxy was in some sense responsible for these periodicities. Well, I was curious. Yeah, you sound like you're familiar with this work.
And very skeptical.
Yeah,
and very skeptical.
I'm a little skeptical. And I'll give you one counterexample. I have a hard cutoff at 5:30, so I'm going to have to go at that. But I'll give you one example. Again, and it's related to the ice cores. If you go back about 40,000 years ago, there's what's called the Le Champ or the Le Champs event, and as far as we can tell, what happened was that there was an almost reversal of the magnetic poles. Right, so the magnetic poles over time have reversed many, many times. The last time they reversed was, like 800 and some thousand years ago, the Bruns Masayama. But 40,000 years ago, they almost reversed. And so what you can see in the records is that the main magnetic field went to almost nothing. Right, and for about 10,000 years it was very small, and then it went back to the way it was. Right, so it's like the poles kind of like almost flipped and then came back. Right, and that's a great natural experiment. Right, so you say, okay, well, so there was no bipolar magnetic field, right? So you would expect a big increase in the amount of cosmic rays, right, which are shielded both by the sun's magnetic field, but also the Earth's magnetic field. And so you'd say, okay, well, where in that particular period is the evidence for any changes in climate or anything? And there's nothing.
I guess that assumes that you have a continuous stream of cosmic rays. That's more
you do, yeah. So the cosmic ray background is everywhere all at once. It's not. There's no. You're not looking at individual supernovas and things. You're looking at the whole suite, and we're getting cosmic rays from all directions.
That doesn't appear to be the case. I'm looking at graphs right now, and it cycles.
Yeah, I guess that's the primary foundation of his argument.
The cosmic rays cycle on Earth because of the activity of the solar field and activity of the geomagnetic field. So there's an 11-year cycle in cosmic rays hitting the Earth, but that's because of the modulation of solar activity.
I guess the basis of Nir's argument was that we experience more of these cosmic rays when we're in the dense regions of the galactic arms, and as we're traveling around the galaxy, we're spending time in more dense regions and so forth. So it assumes some inconsistency.
Before this conversation with Nir Shaviv, I had thought that the solar system stayed in one bright or dark spot in the Milky Way.
Yeah, no, I think we're moving relative to the galactic center.
Yeah, which I had no idea. And we're transiting through the arms, and so the conditions under which we find ourselves change as we transit.
It's plausible. I mean, that's a theory. But on the short-term basis, where we've seen large shifts in cosmic rays, you don't see any big effects in climate as far as we can tell.
Fair enough. Yeah, I think it takes 260 million years or something to go around the galaxy. It takes a long time. I don't quote me on that.
It's along those lines, and so our ability to even put together a global temperature curve on those timescales is very poor. But we're working on it. We'll see.
Big news, everyone. We have officially announced ticket sales for Demysticon 2024. This is our first scientific conference, and what we're going to be doing is we are bringing together our favorite podcast guests in Austin, Texas, April 7th and 8th of 2024. And we're going to have a slew of incredible speakers. For right now, we don't have everyone confirmed, but of the ones that we do have confirmed, we have our favorite scientist, Pierre-Marie Robitaille. We have ancient mythology scholar John F. White of the Craigenford YouTube channel. We have Ogi Ogas, consciousness researcher. We have Steve Keen, economist, and we have many more that are on deck that we will announce very, very soon. So check out the link in the description, and we hope to see you in Austin, Texas of 2024.
Yeah, man, I appreciate you coming by. Is there anything that we didn't get to set straight that you wanted to say before you have to jet? Because, I think this is, I definitely, again, want to thank you for coming back. I think this is the way to do it. Like, if you've been on our show and you feel like we're misrepresenting something, come back, like, set it straight. I think I want to see more of that in the public sphere. I want to see people, I want to be a place where people can sort out ideas, not just defend them and disappear into the void. So,
right. But there's a lot of, as Anastasia said, there's a lot of things that are layered on top of science that are not science, and I think that it's useful for people to try and separate those things out, and to not, the fact that the wealthy people travel on planes. That doesn't say anything about the radiative properties of carbon dioxide, right?
No, but it does say something about the way that the future will play out for the regular person versus the rich person.
Well, I think that's always true, right? The rich are not like the rest of us, right? So they're not any happier than us, though. That's good to know.
Actually, I remember reading that study was fundamentally skewed by some percentage of people that are persistently they just suck. They hate everything no matter what their circumstances are. And that when you remove those people from the calculation, your happiness increases linearly with income. And there's no ceiling.
Not unlimitedly.
I know a lot of miserable rich people personally, so
I know a lot of miserable
anecdotally.
Yeah. I've met a few billionaires. They've never struck me as particularly content, but what do I know?
Well, we'd love to have you back again. This is an endlessly fascinating question for us. I think that it is at the center of just everything in our world right now, and I think that at the end of the day, this is a civilization that is worth protecting and worth saving.
I think so, and that's absolutely. So here we're totally in agreement. I think that there are real threats to what we're doing and how we're doing it, and I am trying to help people make decisions that are going to minimize those risks. It's really a problem avoidance strategy, and if I can help you out, if you have any other questions, or if something comes up, or you want to have somebody argue about some of this stuff, I'm happy to be here. I'm not doing it to sell my book. I'm not doing it to sell my ideas. I'm just doing it because I really think that we have learned a lot, and what we have learned is concerning, and so I like to share that.
Right on.
Excellent.
Well, maybe we'll even get you and Lindzen in the same room at some point down the line.
No, he doesn't think I'm clever enough for him, so it's funny. But one of my only direct interactions with him was a paper that we wrote where we criticized kind of an off-the-cuff statement that he made about how important carbon dioxide was to the greenhouse effect, and he was one of the reviewers. And we came up with a number that was like 10 times bigger than what he had said, and he just gave the grumpiest review, and it took like 4 different submissions to get it published eventually, but it was published and it was right, and he was wrong, and I don't think he's forgiven me.
You always got to have the one grumpy reviewer, though. It just wouldn't be a peer review without it.
Well, exactly. You get used to that. Anyway.
All right,
Thanks
sir.
for having me back on.
Thank you so
Sorry
much.
to cut it short, but
all right.
yeah.
It was great to talk to you.
Okay,
Yep.
great.
Have a great rest of your day. All right, bye everybody.